So recall from our work yesterday with n behavior that we have the following three cases of rational functions. And we actually were able to explore the first case, which is the bottom heavy, which means that the degree in the bottom of the fraction is bigger than the degree in the top of the fraction. If we have a function written in that format, we will have a horizontal asymptote at y equals 0. Case 2. If we have the same degree in the top of the fraction and the bottom of the fraction, what happens is that we get a horizontal asymptote at an equation y equals a over b. The a is the coefficient in front of the highest degree term on the top, and the b is the coefficient on the highest degree term on the bottom. And then the top heavy by 1 we did not get to explore, but we will work with this today and tomorrow. Has a slant asymptote, has an oblique asymptote. There's some diagonal to it, and there's a line with a slant. I drew it with a dotted line because I tend to draw asymptotes with dotted lines. But it's going to be in the format of y equals mx plus b, and we're going to have to find that equation. And we'll get at least a brief start on that today. It says locate, for the examples here, locate the examples, one more time. Locate the asymptotes of the function, draw all asymptotes on the graph, use your graphing calculator to help you plot other key points. And really, in terms of the other key points, I mostly look, can we identify what the x-intercept is? Can we identify what the y-intercept is to help us draw? And I actually am going to start on problem number 2. And then I'll go back and do problem number 1. But here's a function, g of x equals 9 over x squared minus 9. And we need to come up with the vertical asymptote, the horizontal asymptote, the oblique asymptote, and the removable discontinuity, if there is any. And where we're going to start here, even though I didn't ask it, is what's the domain of this function? Where are there gaps in this function? So we take our denominator here of x squared minus 9 to find our domain, and we set it not equal to 0. And we really are better off if we factor this expression, although you could still get the domain from solving that. But it's the difference between two squares. And x times x is x squared, and 3 times 3 is 9, and we need different signs. And then for our domain, we can take x minus 3 and set it not equal to 0, and x plus 3 and set it not equal to 0. And when we add 3 to both sides, we get x doesn't equal 3. And we subtract 3 from both sides, and we get x doesn't equal negative 3. That's the domain. Domain comes from the denominator. That's an easy way to help you remember, because domain starts with d and denominator starts with d. We are not able to cancel anything out in this problem. So our vertical asymptotes are x equals 3 and x equals negative 3. We didn't cancel anything out. So the domain and the vertical asymptotes go together. Now, as we take a little closer look here to determine horizontal asymptote, what we're going to do is we're going to look at the degree of the top of the function. We're going to look at the degree of the bottom of the function. Well, the degree of the top of the function is actually 0. There's no variable up there. It's a constant term, and a constant has a degree of 0. The degree in the bottom is 2. And what we are looking at here is, do we have a top heavy fraction, a bottom heavy fraction, or the same degree? going back to our chart here, which you can see at the top. And what we see is that this problem is bottom heavy. And because it's bottom heavy, again, as I flip back to the chart, the bottom heavy situation means that we have a horizontal asymptote at y equals 0. That may be something that you want/need to memorize. And the good news is, if we have a horizontal asymptote at y equals 0, we don't have an oblique. And also, we did not cancel anything out anywhere. We can't factor the numerator. We only were able to factor the denominator. So we also do not have any removable discontinuity on this one. So the only thing left for us to do here is to draw our picture. But before we do, let's put in our asymptotes. At x equals 3, and x equals -3. And it's hard if you're writing in pencil, but we can also put in our horizontal asymptote at y equals 0. There's our asymptotes. Sometimes what students like to do is they like to use a highlighter to put in the asymptotes. So if that's something that you would like to do, that works for me as well. But let's go to our calculator here and see what happens when we type it in. We can look at the picture. There's our picture. And the nice thing that I can see on here is that we do have a y-intercept of -1. We can graph that fairly simply. And then our other two branches of this graph, if we take another look at it, what's happening is that we have an asymptote on the x-axis, so we don't even have any x-intercepts in this case. So we've got a picture like this, and like that. Let's go back to problem number 1. I know that I went out of order. Problem number 1, again, we need to locate the asymptotes. We're going to draw all of the asymptotes. And then we're going to use our calculator to help us draw in other key points. And the nice part about this problem here on number 1 is that we can't factor 2x squared minus 2x minus 1. If we take a quick look at this, we do 2 times 1 is 2, and the only factors of 2 are 1 and 2. And will 1 and 2 ever combine to be 2? No. So we can't factor anything in this problem. So what we need to be concerned about now is our denominator. And our denominator is going to help us determine our domain. And once again, we're going to set x minus 1 not equal to 0. And then we can add 1 to both sides, so we get x doesn't equal 1. Since we can't factor our numerator, we can't cancel anything out. So, in terms of our vertical asymptotes, we're just going to have x equals 1. And again, we didn't cancel anything out. So we're not going to have any removable discontinuity. So you can put none or NA for not applicable. But then we're gonna go back and look at the horizontal and the oblique to determine whether we have one of those, I should say. And we determine this by looking at the degree of the function. And what we're looking at here is that the degree on the top is 2. And the degree on the bottom is the exponent on the x, which is 1. And we've got 3 situations. We have bottom heavy, we have the same degree, we have top heavy. And in this particular case, we have in the numerator, the top of the fraction, 1 degree more than the bottom. This is going to be a top heavy function. And as we go back and look at the chart here, what it says for top heavy is that we're going to have an oblique or a slant asymptote in the format of y equals mx plus b. And because we have an oblique, we're not going to have a horizontal. And it works the other way as well. If we have a horizontal, we're not going to have an oblique. We have one or the other. Horizontal, no oblique. Oblique, no horizontal. But how are we going to get this oblique, which is going to be in the format, once again, of y equals mx plus b? Well, we have to go back to an Algebra 2 topic called synthetic division. And by the way, if you like the long division will work as well. But synthetic is the shortcut division, which takes a little bit less time. And some of the Algebra 2 teachers set this up slightly differently. But what I like to do for synthetic division is I like to draw an upside down division bar. And what we're going to do is we're going to put in the coefficients from our numerator, the top of our fraction. Remember, if we're missing a term, we have to put in a 0. And our problem needs to be in descending order, which it is. 2x squared, we're going to take the 2 that's out in front of the x squared. Minus 2x, we're taking that 2 in front of the x. And the constant, minus 1. X squared, x to the first 0 degree. It was in descending order. We're dividing by x minus 1. So when we do our synthetic division here, we're going to change the sign. Since it's minus 1, this is going to be a plus 1. And we're going to bring down the first term, which is the 2. That's how we set it up every single time. But if we're missing a term, we have to put in a 0. But now it's going to be 1 times 2. It's positive 1 times positive 2, which is positive 2. And negative 2 plus 2 is 0. 1 times 0 is 0. And negative 1 plus 0 is negative 1. And what we end up with here, or what we started with, is we started with a function that was x squared. When we divide, our degree of our function decreases by 1. So this is x to the first when we divide. So in other words, as I'm running out of space here, what we come up with when we translate that, when we put the variables back into the function, is we get 2x plus 0 minus 1 over x minus 1. We get a remainder. But before we worry about that too much, we want the format to be y equals mx plus b. We just don't have to worry about the remainder. And our oblique asymptote becomes y equals 2x, or 2x plus 0. So now what we need to do is we need to draw a line. We've got a vertical asymptote at x equals 1. And we've got our oblique. And remember that with respect to the oblique here, the slope is 2 over 1. Our y-intercept is 0. Ooh. Supposed to be a b. b equals 0. So here's 0, and it's up 2 over 1, up 2 over 1, up 2 over 1. Or we can go down to the left 1, down to the left 1, down to the left 1. And there we get our oblique. And then we want to finish by drawing this one in our calculator. So I'm going to turn that one on. Turn this one off. In fact, I can clear this one completely. And we can draw a picture. Something like that. Something I will say that I oftentimes check on my calculator is I draw in the slant asymptote on here because I can. Remember it was y equals 2x. Does that seem like it's a reasonable slant asymptote? Yes. And then what we need to do to finish here is we're going to draw our picture. Now I haven't gotten real specific, but what I can see on my graph is that we have a y-intercept of 1. And it looks like that we have an x-intercept of about 1.5. So we'll put those points in. Here's our 1.5. And there's one branch. And then what did I say our y-intercept was? Our y-intercept is 1. So we'll put that point in. And there we get the other part of our graph.